Go ahead and get started. Somebody murdered a whiteboard marker. May you rest in peace.
Broken?
The bottom came out of it. I cracked it and...
It's only a tough time with chemistry.
That's what happens when you chemistry too hard. And I don't see any other whiteboard markers in here. So I'm gonna go grab some. Okay, so what did we talk about last week? Does anybody remember? You had a quiz on it this week. So we talked about processors. Nice, I like how the quiz, and then it was just like, bam, I remember what I did for the quiz. Nice. We talked about GPPs, single-use processors, and then we talked about the application-specific processors. Huh?
I didn't know if I said the acronym right.
You said ASIP, yeah. You nailed it, man. So this is what we dealt with last week, and what we're working on at this point is we kind of dove into Boolean Logic. Because Boolean Logic is itself the foundation of all computing. Most processors are just combinations of NAND gates. So we looked at Boolean Logic and we're like, okay, now you could probably build a very simple large-scale computer using Boolean Logic. That's what people did back in the 1950s. Where in order to do something that in today's world takes almost no processing power at all, it required an entire room. But they did it using Boolean Logic. And once you understand Boolean Logic, then you move into developing Boolean Logic systems where now it can handle putting a lot of information together. What we're working on this week now is we're moving into the physical hardware associated with microprocessors, processing systems, that sort of thing. As we mentioned in the lab last week, and what we're going to be continuing to work on this week, is that when you have a processor and you assign it to do a certain task, there are certain things that the processor is capable of doing on board. It can handle it. It can do those types of outputs. It can do I/O. It can do PWM, for example, on the Raspberry Pi. But it can't do an analog output. That requires a separate chip. It requires a separate system to do that. Well, there are some things that processors can do, but they require external componentry in order to actually operate. So this is where we're going to bring in some definition. So I assume at this point that most of you have done your reading assignments. I know that there's always the person who waits till like midnight to hand it in. But does anybody know what a bus is?
Yellow?
Huh?
It's yellow. Usually someone tired.
It's usually an old guy who has to open the door.
There's a TV show about it.
It's the starting scene of Napoleon Dynamite. What are you going to do today, Napoleon? Whatever I want, gosh. Thank you, thank you. You're a pleasure to have in class, Austin. Does anybody know what a bus is? This is where everybody avoids eye contact. What is a system bus? In terms of our class, what in general is a bus? Anybody have a guess? Try me.
There's a set of conductors used to connect the CPU to memory.
I'll just steal your definitions. I know, right? It's terrible. Okay, so what does that mean? What does a set of conductors, like what physically would that look like? First of all, what is a conductor? Why would you need a conductor on a bus? It's orchestrating motions across the roadway. Today we'll be driving in Symphony of 8. What is a conductor? A conductor is not a storage, although that was a good guess. What does a conductor do? Well, it conducts, right? So, which means it's a carrier. It's something that conducts electricity, right? This is a fancy way of saying a bus is wires. One thing, I mean, it's a wire. But in today's world, we don't need wires to connect everything because we can create printed circuit boards. Or other connections. Basically, you could consider a breadboard to be a bus or part of a bus system, okay? Because it really is. Anytime you hook up stuff to a breadboard, it is a conductor. That's what it's doing. Its job is to carry information. Information has to flow from one component to another component, okay? So bus design is usually pretty easy to work with, because you usually know, I need this wire to connect to this component. Well, all I'm going to do for my bus is I'm going to build a PCB that's going to connect that pin to that pin. And then we'll just draw the line and it'll be straight and it'll be great. Actually, it won't be straight because it has to take right angles. But that's what a bus is. It's just a way of connecting things. So in a computer world, it doesn't really matter if a bus is a set of wires. It doesn't matter if it's one of those flexible computer cables. It doesn't matter if it's an actual printed circuit board that all the components sit on. It doesn't matter what the bus looks like. All that matters is that it is capable of carrying information, okay, and that it's probably yellow. That also matters. Although some people have red buses. Okay, so this is kind of important to any processing system because the bus is kind of, it serves a number of different functions. For modern computers, the buses typically tend to be the physical structure that holds up the entire board. When we use breadboards in our designs, we're actually mounting the components directly to the breadboard. The breadboard holds everything up. It's got all the wires sticking out of it. It's actually holding everything up. And that's what a lot of the bus is used for circuitry, is it's actually a structural component. So let's talk a little bit about PCBs here, just because that's relevant. I wonder if I have one. I have one. I have a bunch. And these are giant. This is what the, I'm gonna hand one to all of you just so that you can look at it, because I have a lot of these. But this is just some circuit board. Now this is like 15, 18 years old. It was produced by Motorola. I got two more for you guys. I didn't count when I pulled them out. Yeah, this is the predecessor to the Raspberry Pi. You'll notice it has a computer output. It has a number of different input-output pins. I'll grab one for me too. But this is at this point, this is old technology. There's a reason why I never asked to use any of these. Now, if you look at everything on here, all of these pins, which I guess I'll show just to the camera, there are input-output pins. That's what the weird-looking things with the metal on top are. Those are input-output pins. You can actually plug components into those. Some of them you can actually plug in. I think these are actually able to be plugged into like microchips. You plug them in. You have some that are able to be plugged into wires. You have a bunch of different resistors, capacitors. You got a couple processors on here. You got one MOSFET up the top. Looks like you may have a, that's a potentiometer, the blue thing. Lots of different components, and everything is mounted to this board. And if you flip it over and look on the other side, there's solder everywhere. Every one of those components was soldered in, likely by an automated system. But you'll notice that there are lines on it. There are different connectors. On the front side, there are also lines. Those are less prevalent, but they still exist. This is the bus. And all of the connections are made on either the top or bottom of this board. Okay, somebody had to look at this and they said, well, we need this to connect here, this to connect here. They had to draw it up in some kind of modeling system, and then they had to actually print it. And they had to print this en masse because they produced a million of these, and these were state of the art at the time, like 20 years ago. In today's world, they're useful for looking at, does it fit in your pocket? Yeah. By comparison, the Raspberry Pi is about a third of this, and is about 20 to 40 times more powerful than this. So, yeah, technology. You'll also notice that this uses the types of resistors that we've been using in class. Whereas if you look at an actual Raspberry Pi, I think I have a bust one somewhere that I could grab. Oh, that's not gonna help. Dang, I got one on my desk. you'll notice on this Raspberry Pi, it does not have those resistors. So does this Raspberry Pi, do they not have resistors at all? Go ahead and pass these around, just comparing the two. Do these have resistors? What?
Can you have built-in resistors? Yes.
You can. But which of those components are the resistors then? Vishay is a local company, and they've been making electronic components like resistors for decades. And one of the revolutionary pieces that they created was they turned this component into one of those really tiny squares. Those tiny squares are resistors. Okay? What do resistors do again? What? Well, they do resist. They're part of the resistance.
They resist voltage.
They resist voltage, which has what effect on the overall circuit?
It makes it so it doesn't have excessive amount of power.
It does reduce the amount of power, okay? So these, they didn't remove resistors from Raspberry Pis. What they did was they took the resistors and they made them a lot smaller. The resistors now are so small that they can embed them inside of processors. Where the processors are smaller than the tip of your finger, they can put resistors inside of them because the resistors now are small enough to be able to do so. Now, there's a bunch of resistors there. All those are used for is to reduce the power that's actually being used by the component. Okay? Reduce the power that's being transferred between pins. This is a highly optimized device, the Raspberry Pi is, that now represents, well, I guess that's not quite state of the art because those are 3B pluses, and they have put out Raspberry Pi 4s, but they're close to the state of the art of what we can do with modern processors. Okay? We have reached that state of technology where now we've taken this thing, we have made the individual components small enough that we can put them on a smaller board. Now, you will notice if you're looking at the Raspberry Pi, a Raspberry Pi still does have the wiring connections. Now, they're actually a lot closer together than these because the components are smaller. In order to fit the processor on the Raspberry Pi here, the processor is connected with what's called a through pin, which means that this component here, it is actually soldered. Like, I don't know how many of those there are.
At least 3.
There's 40 pins. 40 pins soldered onto this processor, which there are 40 pins soldered onto the processor on the Raspberry Pi as well. However, this isn't, this processor uses through-hole connections, which means every one has to be soldered on. Modern processors are actually baked onto to their components. They basically put them in the right place, and then in the right place there are little pockets of solder that connect to your PCB, and then you just place that chip on, and the chip usually has a number of wires going this way to each one of these, this way, and then it's got the chip in the middle. And then what they do is they just heat this up. The solder on those connections then melt and connect to the pins. They will do some kind of a check, a physical system check, where they will touch different connectors and make sure that the processor adhered correctly, that all of the pins had proper adhesion. And then that's it. That's all they do. This is a much more efficient system and produces a lot smaller stuff, allows us to connect circuitry. So PCB design has been revolutionized by smaller components and different methods of soldering components to the board itself. All of these, I mean, you guys could build this yourself. The components that are available to you are much easier. The Raspberry Pis are not components that you could probably build yourself. This is something that you would prototype. That is something that you would end up developing through with a team, or hopefully not by yourself, but where you'll require some manufacturing processes to actually put the components directly onto the board. Okay. There are, right. So I guess to recap, PCBs are boards that are usually comprised of a fairly inert insulating plastic. But it also has copper leads that are directly printed on top of some of the plastic. It's not always copper, but copper is the most efficient one. Usually what they will do is after they print the copper on it, they will actually coat it with another coat of plastic so that you don't accidentally cut the copper or something. Just gives a little bit more protection. These boards are often, in today's world, are made of, they have fiber built into them, they have plastic. Try to protect them, give them a little bit more structural rigidity. I am afraid to flex this thing because I just heard it crack. But boards, they do have a little bit of a flexural strength to them now. The board materials themselves are fairly regulated. I've seen red boards, I've seen green boards, that's pretty common, that's what all of these are. I have seen yellow, but green tends to be the go-to color. I am not certain of the reason why, and I don't care enough to go look that up and find out what that is. But printed circuit boards are usually the connections usually occur on multiple layers. Okay, on this board, if you were to flip it over front and back, you should be able to see all of the connections that are present. On the Raspberry Pi, if you flip it over, you'll see some of them, but you may not be able to see all of them. Although there are a whole lot on the back side. So that's pretty neat. You might be able to see all of them. In some printed circuit boards, they actually have layers where the connections occur inside of the board itself. A little bit more protected than just simply on the top and bottom. Those types of systems can be really difficult to work with because it requires very precise machining, which is one of the reasons why the Raspberry Pi is only on the front and back, which I didn't realize that. That's pretty neat. You'll notice this one still does have some through-hole information. All of these USB ports are through-hole connected. But usually what you'll have to do is you'll have to design the connections on multiple layers. Why can't we just do all the connections on the top side of the board? Why do they do it on two sides of the board? Why not just one? Huh? Well, if you look at the Raspberry Pi just makes thinner wires, which that works too. As long as you're regulating the power through those, you can make them thinner. Light travels, the electrons travel through those wires at the speed of light, regardless of the width of those wires. It's not always about space. There's a different reason. Okay, let's say I have a printed circuit board like this, and I have some through-hole pins over here, and I need this pin to go to this resistor that's up here, and then I need it to go down here because it's actually going out to one of my I/O controllers, okay? Right? That works great. Well, now I have a Wi-Fi Bluetooth module over here. Okay, and this Wi-Fi Bluetooth module has to connect to this component right here, which serves as another I/O port. It's the communications hub, basically. I need to do this, but I can't do that because both of my wires cross. Okay? Any PCB designer is going to run into this struggle. How do I make sure that these wires don't cross? Because as soon as they cross, if all of those were printed, all of those are connected. Which basically does nothing now, because now all of them are trying to send different types of information. It's fine when they're all connected to like 5-volt power. It's fine when they're all connected to ground. It is not fine when this one's trying to transmit data and these are also. Or this one's 5-volt power and this one's trying to transmit data. Okay? It is not okay in some applications for these wires to cross. Which means in order to make this work, if I were to keep that line present, I would have to run a line that goes all the way around like that. Which that's probably not the most efficient way to do it, because it would probably just be easier to, you know, just have it come out of the resistor, come back around here and go like that, and then you can connect these directly. Okay? Designing the physical componentry and designing your bus, it really does take a lot of work. Buses don't get enough credit. Yeah, just no credit. So the stress those guys have to go through, yikes. So one of the things that we will be doing in this class as we move forward on your project is you are going to be required to design a PCB. In doing so, you'll have to design both sides of your PCB to ensure that you have the correct connections. Okay? Now we're probably going to be much like this in that in order to do it, everything is going to be through-hole rather than the more optimized connections that the Raspberry Pi has. So ours will not be the most optimized systems, but I do want you to understand how to design this, how to make a PCB work. That's going to be happening, I believe, starting next month. We'll get started on PCB design. I actually really want to print PCBs as a part of this class because that sounds super fun to me. We don't have a PCB printer, but I know a few people who do, and I also know some places where you can design them, send them in, and then they'll print them and send them back to you. Which, depending on the cost, we may go with something like that. So, okay. Does everybody have a pretty good understanding what a PCB is? You've all touched at least 2 PCBs today, so hopefully that helps a little bit. Okay, now does everybody have a really good idea of what a bus is?
Yellow, magical.
We have not progressed in this class. I'm just gonna pull this out real quick. This is also a bus. You notice it's comprised of wires. These wires do nothing more than connect components together. Okay? These components here, there's no processing going on inside of this T-cobbler. I had to look at it to make sure that I'm right. All that it's doing is it is transferring information from the 40 pins on your Pi to 40 pins on this thing. That's it. That's all it does. This is also a bus. This component is a bus. This component is part of the bus. They're all just interconnected, okay? So a bus doesn't necessarily need to be a PCB. It can be other connections. You can do it with wires, okay? You can do it with physical components like this that actually connect to connect, okay? It doesn't always have to be a PCB. There are ribbon cables present in every computer. You take apart a phone, there are ribbon cables present in the phone. And the reason why there are ribbon cables present is because ribbon cables are themselves very thin. They give flexibility of components, but one of the things that is required out of a ribbon cable is a ribbon cable is inherently flexible. Those ribbon cables that you all have with your Pis are flexible. Okay, that's a good thing because it means that your breadboard and your Raspberry Pi do not have to be on the same plane. You can flex them relative to each other, you can twist them, it's not going to break anything. Okay, with your phones, with a lot of these physical components, you have ribbon cables present because a lot of it is because you have to be able to assemble it. So let's say I have two different PCBs here, okay? This one's gonna be my CPU or my GPU. This one will be my Wi-Fi slash Bluetooth. Maybe I have another chip down here that is just for audio output, okay? If I put these all on one chip, it's gonna make it larger. Okay, if I put them on different chips, I can stack them on top of each other. As long as the connections don't touch, I can put this here, that one over here, and now it's a lot more compact. Just make it a little thicker, but it doesn't have to be wider. Okay, a lot of phones will use this because you have a giant battery that goes on first, and then they'll have a big board that contains most of their processing units. And then they'll have other components that are just sitting out here that fit into little plastic pieces on the screen because they're part of the screen control. So when you crack it open, you'll see the two sides. The screen is connected to the back side where all the components are, where the battery is, but they're connected with ribbon cables. And that allows you to actually open it without shattering the unit. The ribbon cables connect the different components. So ribbon cables are still heavily used. They have these really tiny connectors for a lot of ribbon cables that come in, and all it is it's just like 4 or 5, 8 little pins that are soldered on the end of it, and you plug it in, and there's this little hole that has this thing that you push in that just latches it on, and that ribbon cable is connected. You flip this thing up and you can pull the ribbon cable out, put it back in. It's kind of fun. If you ever get an old phone and you don't want to make any money off of it, you can disassemble it and play with it. It's really fun. You do have to use a heat gun though. It's good learning opportunity playing around with some of that technology. Okay, so that's my conversation on buses. Let's talk about registers quickly before class ends. Okay, so a register is, in a traditional sense, a register had to be, this is where they used like vacuum tubes or they used heavy capacitors, where a register was just a place to store a piece of information. Okay, so a register, oh my goodness gracious. Yep, that did not make it better. Let's see if this can just come back to life later. So basically what a register is it's memory that needs to be utilized immediately. Okay, and as your reading mentioned, there are 3 different types of registers. One of them is the one that's currently being accessed by the processor, etc. One of the issues that happens in any electronic system is electrons travel at the speed of light, which means if you institute a voltage and then all you have is a couple of electrons traveling from, if you have so here you have your memory. Okay, the memory gets accessed. It sends out whether that pin is on or off to the processor. Okay, which that happens at the speed of light, which is basically instantaneously. If this information is not immediately stored, what you have is you have this, where here's your voltage reading versus your time. You have an instantaneous transmission of voltage that immediately leaves. Okay, you have to have some place where you can connect your processor to something that can hold it just long enough that it can actually use the information. Okay? Otherwise it's, hey man, you want to hand me that ketchup? Throw to you, explodes on impact, you don't get any ketchup. You know? You have to be able to hold it long enough to apply it before the ketchup explodes. So that's kind of how this is. What a register does is it allows you to have some finite amount of time where that voltage is present. Rather than just an instantaneous on-off, it gives some finite hold time to it. And now, based on how your processor empties the register, you may have a voltage present for a long time. It doesn't have to be there just momentarily. It can be there for a while. But it's your processor really has now control over accessing the registers to use that information. Okay, so there are a few different types of memories. There are a few different ways they're used. The book presented that well, but that's ultimately what a register is. It's a component that holds information. A lot of processors today have registers built into them, which is why if you go onto this device, you're probably not going to find where a storage unit is. You're not going to find where the memory is. It's built into this friggin' massive 40-pin monstrosity. So I think I could pull this out. Probably shouldn't, but I think you can. It's built into the processors in today's world. Okay, because if the connection between the processor and the register is broken, your entire system is trash. Most connections are pretty, most connections, if you sever one connection, the rest of the system can kind of still work. But the registry, it's because you have a processor that may be requiring 8 bits or 32 bits processing, it has to be able to access 32 pieces of information simultaneously, and it needs to have that information available to it for enough time that it can actually use it. Otherwise, it invalidates absolutely everything. So processor registry combinations, it makes sense to put them in the same chip where they're more protected that way. Which is why modern processors have registers. Okay, any questions on this material? All right. I'm going to give you a reading assignment for next week. I'm going to give you a quiz for next week. We're going to keep working on the design problem from last week this week. Hopefully everybody's pies are updated by now. Hoping. But other than that, you have 2 assignments. You have 3 assignments due tonight. you have to pick your IT sensor. So as a part of your system, I am expecting you to just pick, here's what I want to do, okay? Now I'm going to look at everybody's ideas, and you can pair yourselves up, which I would hope so. So this is supposed to be a group project. You will need to pair yourselves up with somebody or with 2 other people. I wouldn't be too upset if you do groups of 3. But you will need to pair yourselves up, and we're going to get started on picking the components that are needed, looking at all the programming, all of that. I believe the topics for next week are actually how to program processors in assembly language. So things are going to get real next week, because that's gross. All of you who love programming and who love programming in very hard languages, assembly is very hard language.